You're listening to The Solution, a podcast by Growers Mineral. I'm your host, Russell Bobel. In this ongoing series, we will be taking a look at the book More Food from Soil Science, a book written in 1965 by one of Growers' co-founders, Dr. V.A. Tietjens.
Chapter 1. Abundant crop production and good nutrition must be well integrated. It is a safe assumption that there are some things affecting crop yields about which we can do very little. A bushel of corn or other grain crop is made up of starch and storage protein. A bushel of corn, 56 pounds, is made up of 6.7 pounds of storage protein, which in turn is carbon, water, nitrogen, and many minute quantities of minerals, including phosphorus, sulfur, manganese, magnesium, and calcium. These minerals probably account for less than an ounce of the dry weight of the bushel. Water accounts for 8.4 pounds. Starch, oil, and other carbohydrates, including a little fiber, account for 41 pounds. Carbon, taken in as carbon dioxide from the air through the leaves along with some water, is converted by means of sunshine to sugars. These sugars are then converted to proteins. Clearly, the process of growing a bushel of corn is largely dependent on weather conditions, factors not controlled by the farmer. And although the farmer can't do much about controlling the weather, he can learn how crops respond to the different conditions. This in itself is a worthy subject for further fundamental research. Also, to make it possible for the plant to grow most efficiently, the farmer can set the stage by making the soil suitable for the proper growth of the plant. What he does about supplying limestone, plant nutrient materials, and oxygen can be the factor that determines how big a yield he will grow, how good the feeding value is, and how economically he can bring about the process. These are the most complicated problems with which he is faced. He must try to evaluate not only the factors over which he has no control, but also the factors that he can control. After 100 years of research, our average yields are too low to ensure a farmer a profit. The level of fertility in soils has a direct relationship to our future food supply. But the importance of the application of commercial fertilizer in assuring our future food supply and its rankings in the evaluation of the many factors that have a bearing on our maximum yields are questionable. The application of lime to the different soil types and the use of lime in its various forms are a subject which we have recognized for many years, but about which we know very little. We have taken the stand that lime is a necessary evil. But observations I have made and much good supporting evidence suggest that it may be the key to the fertilizer program of the future. We have done very little about integrating the factors that have bearing on the yields of crops. As a result, much superficial research of a testing nature conducted during the past 75 years is worthless today. Soil fertility problems are being discussed from various angles without regard to soil saturation with nutrient ions, the availability of those ions to the growing plant, the acidity and alkalinity of the soil, drainage, aeration, topography, and general location. Even though we have conducted experiments for many years, we are still at the point where we can say only that results were obtained in such a location under the following conditions, which should be named, and that if we would corroborate such results, we must be sure that the conditions of environment are identical. Unless we do, we will get different yield results. Because weather conditions vary from year to year, it's almost impossible to get the same results with a given fertilizer in succeeding years. We have accepted the need for commercial fertilizers because of 80 years of common usage with no questions asked. How much we must depend on the addition of fertilizer nutrients is something which we still don't know. Everyone dealing with fertility problems has in mind the possibility of placing the whole fertility program on a balance sheet basis. In other words, know what is required for a crop, test the soil, know the amount of fertility or nutrients available, and the amount needed by a plant to produce a given crop, and, by arithmetic, apply the difference from the fertilizer bag. To make this possible, we must start out with one absolutely homogeneous soil and completely understand the chemical changes that take place under variable weather conditions. We must be able to forecast the weather for 6 months or more. In some areas, which depend entirely on irrigation for moisture supply, this would seem to be relatively simple. But there are research problems even where we have moisture under control. At one time, I was involved in a cooperative experiment studying the optimum distance that potatoes should be planted apart. The experiment was conducted for 6 years. Different locations were used each year on what we thought was homogeneous soil, purposely keeping the plots small to reduce heterogeneity. We found out many things, but we could not tell at what distance apart potatoes should be planted because every year our results were different. There were too many variables, most of them unknown. It reminded me of a paper I was once asked to comment on. It was a study on the effect of environment on the yield of navy beans. I don't believe that any scientist, even with all the luck in his favor, could solve this in a lifetime. This man had collected data for 3 years, but had nothing to show for his work. Even to study one factor, such as light intensity, cloudy and bright days, could have taken a lifetime. I don't want to seem pessimistic, but I think we try to bypass the time element by trying to solve everything in 1 year. So it is with our soil fertilizer problems. We try to set up a balance sheet on soil fertility before we know what the variables are. There is considerable controversy about the application of facts gleaned from sand culture experiments to soil-grown crops. We might just as well argue the point between loamy sand and clay soils and muck soils, or soils in northern Maine and those in southern Florida. Somewhere along the line, we have missed the boat because we are still a long way from predicting what a crop will do on a given field, even though we do have soil tests, ample fertilizer, and a good moisture supply. We must admit that sand culture does at least give us a chance to start from scratch. By at least partially controlling the environment and eliminating soil complications, we can obtain data which we have a good chance of duplicating if we repeat the same experiment under identical weather conditions. This is almost impossible on a soil. Data to show how much nitrogen, phosphorus, and potash is needed to produce a pound of corn under a given set of conditions can be obtained with sand culture. All we need is a large number of pots or containers. By varying each factor in sufficient numbers, we can arrive at such a figure. We at least have some information which we can put down in the record under one set of light values. If we add one additional variable, such as 2% of organic matter, we have complicated our experiment. What do we do with that data depends on our knowledge and experience. Perhaps on a sandy soil with no profile differentiation, we might be able to duplicate the results in the field if our moisture supply is adequate. Perhaps we could do this on a soil with slightly more silt in it, or even more clay. Or we might even allow for some additional organic matter. Where can we draw the line? If we could run the same experiment on 100 different locations and obtain on 75 of them positive results that agreed with our original data, we could feel that we were making progress. Such data would give us considerable confidence in what we were doing. If we could get 75 out of 100 to show some similarity in a definite response, we would have an exceptionally good batting average. But 50 out of 100 comes closer to present achievement. This gets us down to a 50-50 basis, a guessing basis. A large number of experiments can take much guessing out of research if there is some similarity in the results. If experiments show big differences in yield, we can have more confidence in our results than if we use statistical methods to find out whether we have something or nothing. Some years ago, a friend of mine showed me some data on sugar peas. In 2 out of 5 years, he had gotten a negative correlation, while in the other 3 years, he had gotten a positive correlation. He insisted there was a positive correlation. Statistically, yes. Practically, in my opinion, the wastebasket was the best place for the data. To minimize field variability, I have assumed that it is wiser to replicate experiments 100 times to get an average trend rather than depend on one experiment for more exact data. I prefer to conduct the same experiment in 100 locations under the same seasonal weather conditions. If 90 of those fields show the same trend or similar results to a given treatment and only 10 show a variable response, I assume there is a definite response to a given treatment. It seems to me that if, when we are conducting experiments, the magnitude of difference must be determined by statistical methods, we are not treading on very sound ground, particularly when our yields are near average for an area. In other words, I cannot get very enthusiastic about 10 bushel yield increases for an area. It means we have not found the real cause of low yields. If we are going to help agriculture, we must get yield increases sufficient to reduce unit costs materially. In most cases, this means more than doubling existing yields. It has been my privilege and pleasure to work with outstanding men in the scientific field, as well as with many critical, progressive farmers. As a result of my work with people in various parts of the country, I have formulated some definite ideas, which in some cases have shaken my faith in past research on crop production. It seems to me very difficult to establish facts. There are so many variables to contend with that, at best, our results may only be a good guess. That a man can grow 300 bushels of corn on an acre doesn't prove anything. It simply means that he had the majority of variables in his favor. As one farmer told me, whenever he figured he knew how to grow a 200-bushel corn crop, he would get 75 bushels the next year, with practically the same treatment and rainfall. But I am convinced there are some good reasons why our average crop yields are too low to return a profitable labor income to farmers. Average crop yields, even though they do not return a profit to the farmer, may in many cases been sufficient to maintain natural surpluses, which in turn have demoralized farm prices. It is my opinion, after many years of experience, that these average yields could be doubled with very little effort. The question arises as to why it has not been done, and whether it should be done. I am only interested in the former. Our economists must grope with the latter. My main concern is to help the farmer to grow a crop so that he has something to sell at a profit. He at least won't starve. Why do we have such low average yields? Either the farmers have not listened to recommendations from the personnel in their advisory systems, or the recommendations have not been sound. It is probably a little of both. As I contact members of our farm population, I realize there are some who don't care. They usually squawk the loudest for government help. There are some who are confused. They hear so many different ideas that they usually do the wrong thing. Then we have the chap who is very conscientious, who believes everything he hears, and when he gets enough, his acre costs are so high that even good yields bring him small profits. A good example is the experience of one grower who cooperated with me for many years. He found that adequate limestone could increase his corn yield by 45 bushels. Subsoiling his fields added another 17 bushels. Minimum tillage added 21 bushels. Plowing his ground and planting corn immediately without preparation when the soil was free of excess moisture added another 13 bushels. Planting more seed per acre added 11 bushels. Using fertilizer solution on the seed added 10 bushels. And applying foliage spray 1 to 3 times added 10 to 25 bushels. The highest corn yield he harvested was 198 bushels, where 5 years before he was harvesting 50 to 60 bushels. If he had left out the limestone, he probably would still have only 50 to 60 bushels, even though he did all the other things. He said you can't leave out part of the practice if you want big yields. I visited a man who was bubbling over with excitement because he had a beautiful field of corn with a potential 100 bushels per acre. He told me that he plowed the ground and, without further treatment, planted corn. Then he sprayed with a weed killer. The field was clean. He used 20 pounds of 10-20-10 in solution when he planted his corn and sprayed with 20 pounds of fertilizer solution when the corn was 3 to 4 feet tall. He said, "Think of it. I don't have $20 an acre invested, and it is the best corn I have on the farm. It doesn't make sense." I told him that it was the type of thing that he would have to do to make money, that he must use his judgment in evaluating what he hears and reads, even though the information may come from a reliable source, that he must expect to grow a good crop with fertile soil. Otherwise, why own high-priced land? Contrast this with the corn farmer who had his experience discussed in a farm paper. He achieved the impossible task of growing 100 bushels of corn per acre, but his fertilizer cost alone was over $70 per acre. After figuring his total costs, his only return was the satisfaction of having grown 100 bushels of corn on an acre of ground. The person who wrote the article forgot to mention anything about costs, but this farmer probably complains that something should be done about the farmer's problem, that there is no money to be made in farming. I have another farmer who had an idea and decided to prove it. His success should merit the highest praise. He bought a farm in a hilly section of southeastern Ohio, which was classed as marginal land. As a matter of fact, he was told that he could not make a living on such land. However, he thought that he knew better. He bought the land and applied large quantities of limestone to the soil before and after plowing, before he planted corn. Several years later, I gave a lecture in his community and stated that if a person could not grow 100 bushels of corn without fertilizer, he had better examine his soil for calcium content. I talked with him after the lecture. He told me that he was growing 100 bushels of corn per acre, and he still had not used a pound of fertilizer. I told him he probably could have made more profit by applying some fertilizer. When I realized that actual facts are hard to establish in a field where so many variables exist, I began to wonder whether we know anything about crop production. To me, the disturbing thing in crop nutrition experimentation is when I take for fertilizer comparison experiment what seems to be a poor piece of ground and find that the plot I left with no fertilizer yields as well as the one I used fertilizer on. I have had this happen with many different crops. During the years I spent conducting fertility investigations in the coastal plains soils of New Jersey and Virginia, I found that it was virtually impossible to get worthwhile results from plot experiments unless I first investigated the subsoils to see whether the chemical and physical condition of the subsoil would permit a crop to grow. If the roots could not penetrate the subsoil, there wasn't much use in conducting an experiment on fertilizer comparisons in such a location. Dr. Jacob Jaffe from the Soils Department in New Jersey and I conducted an experiment on sweet potatoes in Lakewood sand in the 30s. We found the 8 inches below the surface to be very low in calcium, so we applied 1,000 pounds of pulverized limestone per acre in the bottom of the plowed layer as the ground was being plowed. We did this by hand on all but 3 check plots, which received no limestone, when we plotted our fertilizer treatments in triplicate over the field. In spite of the fact that we had widely different fertilizer treatments, the only plots that showed any difference were the check plots where we had placed no limestone. Here, the yield was less than 100 bushels compared with yields of 300 bushels, plus or minus 9 bushels on the other plots. Where we had placed limestone in the bottom of the furrow, we had deep root penetration, whereas on the plots where no limestone had been applied, we had no roots below the plowed layer. Adding limestone was more important than the kind of fertilizer we used. Lakewood sand is a seacoast deposit which has no profile differentiation. These soils are considered very poor for crop production. Because of the openness of these soils, it was considered imprudent to apply fertilizer anywhere, except in a thin band alongside the plants. Upon careful consideration, it was decided to place the fertilizer deep in the soil, 12 inches to 16 inches in the subsoil, directly under the row of plants. The reason for this was the fact that nutrients move to the surface during the growing season. Except in the hurricane season, the amount of rainfall is not enough to cause leaching. Therefore, the fertilizer left on top never made contact with the roots. It stayed in the surface and caused the roots of plants to stay near the surface, where they soon became short of water, causing the plants to wilt. When we placed the fertilizer deep in the soil, we were surprised to find that the plants did not wilt, even in the hot, dry weather. When we harvested the crop, we found that where the fertilizer was placed, deep sweet potatoes produced 3 times the tubers produced where the fertilizer was applied alongside the plants. Tomatoes yielded so well that the grower took in $3 for every $1 where the plants were side-dressed. These results were obtained where fertilizer was applied. Where no dry fertilizer was applied, the yield was still higher than where dry fertilizer was applied as a side dressing. Where we used 1/5 as much fertilizer but dissolved it in water, 100 pounds of 5-10-5 instead of 500 pounds, the crop yielded 50 more bushels of sweet potatoes. When I came to Ohio, I assumed that I had left this type of soil, since I was in the western area, where the soils are derived from limestone. I did not expect to find a poor root penetration in the subsoil, but I was mistaken. In August of '56, I saw a cornfield, which I would have bought at 100 bushels an acre in July. But when the corn was harvested, we had 19 bushels of nubbins. I had tested this surface soil and found it a good level of fertility and adequate available calcium. I checked the subsoil after the crop was harvested and found no roots below the plowed layer. The calcium reading was less than 200 pounds when it should have been 2,800. And the soil was too hard to dig with a shovel. The acidity, or pH, was near the neutral point. Apparently, on long-cultivated soils, one cannot take much for granted. I brought some of this subsoil into the laboratory for a preliminary test, determined the calcium requirement, and found it needed 6 tons of limestone to satisfy its needs in the surface acre per foot. I mixed the limestone with half of the soil, filled 6 coffee cans with this mixture, and 6 with the untreated soil. I planted 5 grains of corn in each. There was no difference in the time of germination, but there were 28 seedling plants in the treated and 16 in the untreated cans. Both lots grew equally well until they were 8 inches tall. Then I noticed some marginal browning on the untreated plants, and when they were 16 inches tall, they were yellowish green. The lower leaves had dried. The plants in the treated soil remained a nice, healthy green up to 24 inches tall before they showed any nutrient deficiencies. The color began to fade, probably from insufficient nitrogen, since I had applied no fertilizer up to this point. Then I applied a weak solution of nutrients to 4 out of the 5 cans in each group. Those in the treated soil showed a response in 3 days, but I got no response in the untreated soil. I was surprised that the plants in the untreated soil made any growth beyond what one would expect from the seed. But when you take such a subsoil, pulverize it, and expose it to the air, you usually get a good effect from the aeration that occurs. I have had farmers argue with me that they would ruin their soil if they followed my suggestion that they plow deeper to increase the depth of the surface soil. I feel that when a man can't grow over 50 bushels of corn, he is not gambling very much by turning up an inch of this subsoil unless he is on exceptionally low calcium soil. In this case, the application of 2 tons of finely divided limestone should increase his yield 50 to 100%. This practice could also cause trouble if there was considerable clay and 3 or 4 inches of rainfall in a short time. Low calcium clay can seal the surface so that the air is excluded from the roots. In eastern Virginia, one of the cooperators who followed my advice on deeper plowing and applying limestone deepened his plowed layer to 14 inches and told me he had harvested 80 bushels of soybeans per acre. I did not see the check made on his yield, but I did see the beans before they were harvested. They were in 36-inch rows. The plants were between 3 and 4 feet tall, and the pods covered the stems. So I had no reason to doubt his word. He used no fertilizer. I have seen equally good plants grown where the nitrogen was too high and they produced only 17 bushels per acre. Too much nitrogen has kept many a farmer from growing over 30 bushels of beans to the acre. Last year, I checked a field of green peppers which were in flower. The plants were 2 feet tall. I told this grower he had too much nitrogen and that he would be lucky if he picked any peppers. He told me later that he picked no peppers from this field, but that he did have a beautiful crop of stems and leaves. He said he never saw such beautiful, large, dark green plants, characteristic of plants growing on soils where nitrogen is out of balance with the other nutrients. I traveled throughout the East Coast from New England and northern New York State to Florida and evaluated spinach fields. I found tremendous variations in the growth and quality of the crops. Even though one may not know why the differences occur, one does realize that there must be big differences in soil conditions. Weather conditions can usually be ruled out because good and poor fields occur on both sides of the same fences along the whole region. As I inquired about fertilizer practices, I noticed that the best spinach had the least fertilizer and some of the best quality was in soils that had considerable limestone applied. While I was at the New Jersey experiment station, I conducted an experiment in 2-gallon crocks. One series was growing spinach on adequately limed soil, while the second series was grown on the same soil with no limestone added. Fertilizer placement treatments were comparable on both sides. The available calcium reading on this soil was 400 pounds per acre. The limestone series had sufficient limestone to eventually raise the available calcium to 2,800 pounds. Spinach seed was planted in all pots and thinned to 4 plants in each crock. When the spinach plants in the limestone series were 6 inches high, they were harvested, weighed, and then the plants were dried for dry weight yield. There were no differences between the treatments in the limestone series. The effect of the limestone overshadowed every other variable. In the low available calcium series, it was quite another story. The plants ranged in size between 2 and 4 inches. The best plants were in those crocks where considerable low analysis fertilizer was thoroughly mixed with the soil. Where the fertilizer was placed in bands to one side of the seed, the roots never made enough growth to reach the fertilizer. When I was with the Virginia Vegetable Research Station, a representative from the Beechnut Packing Company came to see me about the idea of canning spinach in the Norfolk, Virginia area. After a 2-week survey, he decided the quality of the spinach was not good enough to meet their rigid specifications for baby foods. I went into a huddle with Dr. L. Danielson, our plant physiologist. We decided to work with several growers who grew over 200 acres of spinach. A survey showed that 1,000 to 2,000 pounds of a complete fertilizer was applied for each crop, and 2 to 3 crops were grown each year. December and January spinach did not grow freely. We found that the spinach went to seed and sent up a seed stalk prematurely as soon as it was ready to harvest, so that the harvest season was less than a week. This meant that the crop had to be dumped on the market without regard to price. Dr. Danielson started by taking samples of the foliage and soil and analyzed the foliage. He calculated the amount of nutrients in an average yield, 300 to 400 hampers per acre, and found 187 pounds of nutrients, which the plants recovered from the 1,600 pounds of fertilizer that had been applied for the crop. Then he checked the soil and found a pH of 6.8, but only 400 to 800 pounds of available calcium. The phosphorus and potash readings were very high. All the spinach roots on this Norfolk sandy loam were in the plowed layer. We decided we needed 2,800 pounds of available calcium on this soil. The grower started to put on limestone at the rate of 2 tons per acre. We also reduced the fertilizer to 500 pounds per acre. In addition, we applied 20 pounds of manganese sulfate in anticipation of a deficiency of manganese because of the heavy limestone applications. We found later that this was not necessary because the plants were getting more manganese as we applied more limestone. This, we found later, was because the roots were readily penetrating the plow sole and were feeding in a large volume of soil. We could see an improvement in the spinach, but it wasn't until 2 years later that the farmer grew his big spinach crop. Before we started, I had told him he should grow 1,000 hampers of spinach on an acre. He looked at me, and after what seemed like too long an interval, he said, "Tell me how to do it. I never saw that much spinach." Just before Christmas of the second year we worked with him, he came into my office with a grin on his face. He said, "I just figured out my average yield on the 200 acres of spinach. I sold 220,087 hampers, or a good 1,100 hampers per acre. Furthermore, I have a letter from my commission man in New York City. He told me my spinach was the best quality that he had ever handled from this area." He had applied 7 tons of limestone per acre and was using only 500 pounds of fertilizer for 3 crops. He said the pH was just below 7.0. This situation is a good example of the problem existing in much of the area on the coastal plain soils: insufficient available calcium and too much commercial fertilizer. Only by adjusting the available calcium in these cultivated soils can we hope to make some progress in determining the fertilizer requirement. We have conducted too many fertilizer requirement experiments on soils where the controlling factor to crop production was available calcium rather than insufficient fertilizer. Many of our potentially productive soils are idle. If one travels over the various countries of the world, one cannot help but be impressed by the tremendous amount of land that is not under cultivation. Some of this is too rough to be cultivated, but there is much that is abandoned land, cut up with fences into small areas. Much of it is old pastures, which are not producing enough grass because the available calcium is too low. Much of the land is level and is covered with poverty grass. This land has a high pH, but needs 8 or more tons of limestone per acre to make it productive. Many people who supposedly have the training to be soil and crop specialists catalog this land as worn out or too poor to be profitably farmed. I have never considered a soil worn out just because it is unproductive. There's nothing to wear out. It may be temporarily depleted in fertility, or it may have been mismanaged and permitted to become depleted or available calcium, thus make it unproductive. I feel a soil is unproductive because chemical reactions are not taking place as they should. If we know of what a particular soil consists, we should be able to get our cars back on the track in the proper order so the locomotive can get them to their destination. This is something that few people seem to be able to do. Too many of our research men get the cart before the horse and then expect to make the horse function properly. In my early contacts with farm people, I was surprised to find that there were people who farmed 160 acres who, because they were losing money, would go into debt to buy another 100 acres, thinking they would be in better financial condition. In business, volume of business usually is correlated with profits. A big overhead cost divided into a greater number of units of production would result in more profits or make it possible to sell the unit at a lower price. In other words, if you add more machines under the same management, you produce more units of production. This can be true on a farm if the farmer is a good manager to start with. But if he can't make a profit on 160 acres, the additional land will have to be tilled by hiring more high-priced labor, and he will still be losing money. Here again, the man's intelligence is highly important. A lazy mentality is sure to lose out. I have worked with people of various degrees of intelligence. One of these, who I felt was not getting out of his land what he should have, with his apparent mental capacity, asked me to work with him. He had read everything he could and was so confused that he couldn't make up his mind what was the right way to handle his soil. Also, he had been misinformed. I told him the first thing was to develop a reasonable philosophy by reading more critically and not believing everything he read or heard. I heard a farmer question an agronomist at a farm meeting as follows: "Doctor, Your statement doesn't agree with the article I read in the farm paper. Can't we rely on them? He was answered, Don't believe anything unless it was written by someone in my department. It has always seemed to me that there is one correct answer to any question regardless of who answers it. So when the man I was working with asked me why he couldn't grow over 80 bushels of corn per acre, I told him his philosophy was faulty because he read things written by people whose thinking was faulty. He had been told that he had sufficient lime in his soil and that he should use twice as much fertilizer. I told him that he needed 6 tons of limestone and that he could cut his fertilizer application in half. When he argued about it, I told him I would be glad to prove it to him by growing a crop with my application alongside his in at least 3 places on his farm. When he harvested his crops, he had 83 bushels, I had 141 bushels. Then he wanted to know why he had been given the wrong information. I told him that the good doctor who misinformed him probably didn't know any better. When he got these results 3 years in succession, he decided to farm fewer acres so he wouldn't have to hire help. And as he told me later, he was making more money. We have too many people in our agricultural institutions and in our agricultural advisory systems who are unintentionally mentally lazy. When they get their college degrees, they stop being students. They have certain fixed ideas in their minds, and when they hear or read something that is at variance with their thinking, they not only refuse to examine it critically, but go so far as to condemn it as propaganda which someone is peddling to sell his product. We have too many people doing research who feel that our salvation lies in the use of large quantities of fertilizer. They are as wrong as the man who claims we can get along without fertilizer. Most important is the discovery of the factors that control crop production. These can be dealt with in their proper order. This requires not only clear thinking, but good judgment and accurate observation. Plot comparisons should be used freely in making decisions. There is one comparison that should always be made, a comparison between 2, 4, 6, and 8 tons of limestone will always yield increases, because it has been my experience that at least 90% of the time, saturation of 85% of the base exchange capacity of any soil with calcium will materially increase yields.
Thanks for listening, everyone, to this episode of The Solution. If you'd like to learn more about the Growers Program or anything you heard in this podcast, visit our website at growersmineral.com. Make sure to subscribe so you don't miss another episode. Thanks. We'll see you guys in the next episode.